G'day. In this series of videos, we are modeling psychometric functions. Our modeling career is really taking off. In the previous video, we learned how to generate samples from a uniform distribution, and we also put that into a function. We called that function, I think, something like subresp, which was shorthand for subject response. And we're going to use this later on. In this video, we're going to do number 2. The second video, we're going to make a Gaussian model, because what we're going to do is we're eventually going to compare our subject responses to the probability that's returned by the Gaussian model. It will make sense in a little bit. So we've got to do a little bit of preparations before we get cracking into the, just tying it all together. All right, so let's make a Gaussian model. Now, if you have seen the previous video that I did, where I talked about probability density functions and cumulative distribution functions, then this will be old hat for you. It should be straightforward. But if you're new to this, let's have a think about what we need to do to generate this Gaussian model. So we're going to do a Gaussian model. It's a cumulative distribution function, and we're going to give it some parameters here, location and scale. All right, so let's go down here. Now, to generate our Gaussian, we will need help from scipy.stats. We'll import a norm, okay? Cheers. So, import scipy, from scipy.stats, import norm, because we're going to use a normal distribution, which is Gaussian distribution. And what we're going to do is we don't need to see this sub-response function anymore, and we probably don't need this. We will need it later on, but let's create another function now. So I'm going to call this model PR. So model PR is going to be from the Gauss. So we're going to start with a doc string, and we're going to return an array of probabilities corresponding to a Gaussian cumulative distribution functions. Remember, the cumulative distribution function is the sorts of functions that we use when we model psychometric functions. This monotonic S-shaped growth function. It's a cumulative distribution function. In this case, it would be the Gaussian. It could be a Weibull or a logistic or a gumball or a reverse gumball or a reverse Weibull or an exponential. Okay. We're just going to use a Gaussian here, or a normal function. Return an array of probabilities corresponding to a Gaussian. Now, because we are creating a Gaussian, we need to give it 3 parameters. We need to give it the range of stimulus values. So if you're running your experiment in real life and you're going to present to your subject, like, say, some soft sounds and some loud sounds, and so you're going to have on your amplifier like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in terms of the volume or the amplitude of the sound, then your stimulus intensities will be 0 to 10. Okay. If you're doing an orientation discrimination task, like for visual system function, where you basically present gratings of different orientations, and you've got a difference between the orientations between, say, 0 degrees and 90 degrees, and so therefore that's going to be a delta orientation of 90, and then you're going to slowly drop it down, so now you've got a delta orientation of 0 because they're both at 90 degrees. Then your stimulus intensity is obviously going to be slightly different. So you need to define the domain of your stimulus array. In our case, we're just going to go between a 0 and 100. So our stimuli will go from 0 to 100, and we'll do it in steps of 2. Doesn't matter. Of 2. This is not our experiment steps. This is just the model that we're using to generate. Our experimental steps will come in later in the next video. And then we need to give the Gaussian a location in this stimulus array, or we need to give it a mu value. So we'll call it, I think Scipy calls it location. So that's like the average value, or where 50%, the 50% point on the CDF. We'll see that in a little bit. So we'll need to give it a location, and we need to give it a standard deviation, which is going to define the slope of the function. So the slope can go left or right, but the slope can either be really flat or super steep, flat or steep, and that's this value called standard deviation. I think they call it scale in Scipy. So we're going to need it. We will need to give it 3 things. So the first thing is we'll need to give it our stim. So our stimuli x it's going to be an array of values, so we'll use numpy dot arrange, and we're going to go between 0 and 101 in steps of 2. Just to see if that's happening, we'll just print out stim x. Now, in order for us to run this, we need to go back to the parent indentation, and we'll call that function model PR, something like that. So hopefully what we should see is an array between 0 and 100 in steps of 2 being printed out. So let's have a look here. I'll just make this a little bit taller. There's our array here, 0, 2, 4, 6, 8, 10, 12. Don't worry about this stuff up here. That's what we ran previously, okay? But this is why we've published this. We print the timeout because I now know that we have run this at 2:14 p.m. in the afternoon. So yep, that's going to be our model is going to be over the X domain or the X array of 0 to 100. Okay, great. This is a good start. Now we need to generate our model PR. So we'll just call this model PR. This will be a Gaussian model. So that's going to be equals the normal distribution, and we want the CDF values, the cumulative distribution function. And we want to generate the model probabilities over the same range of X values. So we'll give it the X value array, okay? And we need to give it the location, okay? And we need to give it the scale or the standard deviation. So we have to come up with this now. So we're just going to hard code this for now. When you do your actual experiment, then you will have to think about defining this. In fact, you'll probably do some curve fitting using like Bayesian inference or something like that to say, hey, from our experiment, we got this curve and our best fit curve returned this location and this slope, okay? In our case, we're just going to hard code this for now. So we're going to say the location equals, say, 45. It's about halfway between 0 and 100. And we'll set the scale to 10. So we'll give it the location and we'll give it the scale. In fact, I'm actually going to call this something different. I'm going to call this mu, or average, and the standard deviation. So instead of that, we'll say mu and SD. And so what should happen now is this model PR should return an array of values from the cumulative distribution function. So it's going to return the probabilities over this range of values for a normal distribution that has a location of 45, because that's what we set here, and a scale or a standard deviation of 10. So we're going to return these values now. Return. We're going to return stim x, so we're going to return the X array that we've given, but we're also going to return the probabilities, so the model probability. So there's two things that we're returning, and so when we run this, we call the function, but since we're returning two things, we need to give it two variables. So we'll just say this is X and PR, like that. So if we plot these now, so this first value here that we return is going to go into here, and the second one here is going to go into PR, okay? And so if we want to plot this, we want to see, hey, what's returned? Does it look like a Gaussian cumulative distribution function with a location of 45 and a slope of 10? We'll plot it. So plot.plot, and we'll give it X and PR. We'll set the color to black, and we'll set the marker to, we'll give it some X's, and we'll set the line width to 2, and the line style, we'll make it dashes, nice and pretty. Now, let's set the X limit. So plt.xlim, we want to plot between 0 and 100 because that's the range, the X range that we are generating our Gaussian function over, CDF over. And we want to plot our Y limit. We want to maximize the appearance of our graph so we don't have any white space anywhere. So we want to go between 0 and mp.max PR. We want to take the values that are in this model probability and we want to set it to the maximum. Actually, I just thought about it. Cumulative distribution functions will only ever go to 1, so we actually don't need to do that. If it was a probability density function, then yeah, we probably would need to set it to the max of the array, but CDFs only go between 0 and 1. We don't need any labels or anything, we just want to see what we're doing, and so yeah, let's show this. Plot.show. So what we should see, if we run this, is we should see a figure appear where we've got a Gaussian cumulative distribution function where the 50% action has... what have I done? I've spelled it wrong. PLT.PLT. So where the x-axis should go between 0 and 100, and the y-axis should go from 0 to 100%, or from 0 to 1 in terms of the probability. Okay, so this is what we have here. Great. Now, I can't really see the 50% mark here, so what I want to do is I just want to go here. I'll quit out of that, and I'll add onto this plt.plot. I want to plot, say, I reckon that the 50% point, so the 0.5 point, is going to occur at 45. So if this is correct, I'll go at x value of 45, we should see the 50% mark. And so if we now set the color now to, say, red, and we set the marker to a nice big circle, okay, and we set the marker size to, say, 4, nice and big, we should see hopefully now a big red circle at the 0.5%, which corresponds to the 50% mark here. And so that's what we've got here. Yep, 50% at 45. So this is good. That's not very big. Let's make this bigger. Let's make this, say, 8. Well, we'll make it 10. All right. So we have now generated our model, our CDF, and we now know that our model is a Gaussian CDF cumulative distribution function with a 50% point, or the location at 45. Okay, and the slope is 10. Now, we can't really easily see the slope in this, but trust me, it is a slope of 10. And what we're going to do in the next video is we're going to go through all of our in silico responses, and we're going to basically convert our responses, our subject responses, into correct and incorrect. Right. We're slowly tying things together, but we've still got a couple of building blocks to go. Leave this video here. Pretty straightforward, really, hopefully. And I'll see you in the next video. All right, see you in a bit.